Today we're going to talk about differential analysis of fluid flow. Here the fundamental differential equations of fluid motion are derived in this chapter, and we show how to solve them analytically for some simple flows. More complicated flows, such as the airflow induced by a tornado here, can be solved exactly, and we're going to get into the other ones that we are what's called Newtonian, and they behave as we expect them to, and then counterintuitively the non-Newtonian as well. Here are our objectives. So we can use a couple of different techniques or paths to solve these analytically. Here's the control volume technique. And this becomes useful when we're interested in the overall features of the flow. So when you have mass flow rate into and out of a control volume, net forces applied to the bodies, things like that. So we're looking at the overall, that's the key here, the overall features here. The differential analysis is an application that involves the differential equations of the fluid motion of any and every point of the flow fluid. So you can think of this as the micro, right? So this one would be a macro because you've got an overall. So you can think of this as a macro view. And then this, alternatively, you can think of as the micro view. And so this is it involves the application. So you're going to be using the differential equations, which is how you get that differential analysis name here, this differential equations of fluid motion to any and every point of the flow fluid over a region called the flow domain. Okay, so you can see that here. So here versus 1, you've got the control volume technique. You're looking at the overall things, mass flow rate in, mass flow rate out here. And that's bounded by that control volume, right? And including the force right here. But when you're looking at the differential analysis, you're looking at everything in between it. You're looking at not only the flow in, but any and every point of the flow fluid over the region. And so this here, instead of it being the control volume, is now the flow domain. Okay? And then you have boundary conditions for variables must be specified at all boundaries of the flow domain, including inlets, outlets, and walls. And you would know that because here the boundary is changing from the control volume to the flow domain and how we use those and how we analyze them. If the flow is unsteady, we must march our solution along in time as the flow field changes. So we would just match our solution or our analyzation with the flow change. So here, of course, with any kind of flows, we also have that conservation of mass, the continuity equation. And so here we have those formulas. And then here, the net rate of change of mass within the control volume is equal to the rate at which the mass flows into the control volume, less the rate at which the mass flows out. So it's just the difference, right? It's the net rate of change here. The rate of change is only what comes in less what comes out, right? That's all we're looking at. Okay? And the derivation using the divergence theorem. And so this is also Gauss's theorem here, and this is it spelled out. So the quickest and most straightforward way to derive the differential form of conservation of mass is to apply this. And then you also have a continuity equation. And this equation is the compressible form of the continuity equation since we have not assumed incompressible flow. It is valid at any point in the flow domain. And remember, we've been using incompressible liquids, right? And so this one is going to be compressible, the compressible form. And then looking at the derivation using an infinitesimal control volume. So when we're looking at locations away from the center of the box, we use the Taylor series expansion, regarding the center of the box here. And then that gives you each one depending on the location. So you can see center right of the face, center left of the face, center front of the face, center rear of the face, center top of the face, and center bottom of the face. And you can see all of these dots here, locating those. And then a small box-shaped control volume centered at point P, so that's the very center, is used for the derivation of the differential equation for conservation of mass in the Cartesian coordinates. The blue dots indicate the center of each of those faces. And here's some more, just showing you the surface area, the average normal velocity component. You've got those front center, bottom center, things like that. Mass flow rate, rate of change, just all of these. And then as well as the net mass flow rate into the control volume. And you're just combining those all together, summing them because it's a sum. And you've got left face, bottom face, rear face, etc. And here again is the net mass flow rate out of the control volume. Right face, top face, front face, etc. The continuity equation in the Cartesian coordinates, and those again are just added. Here's our alternative form of the continuity equation, and it's derived here. And then this is showing you a streamline, and as the material element moves through a flow field, its density changes according to this formula here. And this shows as we flow a fluid element through a flow field, material element, that's what that's called, its density changes. On the other hand, if changes in the density of the material element are negligible or negligibly small compared to the magnitude of the velocity, so if we have a very small magnitude of velocity gradients and a very large amount of that, right? We have the material change. But on the other hand, if it's very small compared to the magnitude or a lot of the velocity gradients, as the element moves around, then the flow is approximated as incompressible. So it doesn't have to have completely no material changes in regard to the density. It just needs to be comparatively on a small scale. Then we have the continuity equation in the cylindrical coordinates. So you have the coordinate transformations here in regard to the x, r, x, y, and theta, and then as well as the continuity equation in the cylindrical coordinates, and you can see those all summed together here and mass balanced to 0. And then you can see, there it is. Oh, it's just taking note back. You can see them outlined here on the XY axis. So A is the two-dimensional flow just on an XY plane or an R theta plane. And then B, you can see that in a three-dimensional flow. So we do always, of course, have special cases, and that's steady compressible flow. And you see that steady continuity equation here. And you can reduce the steady continuity equation down depending on if you're doing it in the Cartesian coordinates or the cylindrical coordinates as well. So here you have the incompressible continuity equation, and that's equal to 0. And then incompressible continuity equation in regard to the Cartesian coordinates, and then the same in the cylindrical coordinates as well. And then the special case number 2, incompressible flow. So the disturbance from an explosion is not felt until the shock wave reaches the observer. The continuity equation can be used to find a missing velocity component. And then here's an example, the comparison of the continuity and volumetric strain rate. And so we've worked the volumetric strain rate and in the Cartesian coordinates. And what we have been able to find is that for a final result in general, not limited to the Cartesian coordinates, it applies to unsteady as well as steady flows. So here is A. In an incompressible flow field, fluid elements may translate, distort, and rotate, but they do not grow or shrink in volume. And then in B, in a compressible flow field, fluid elements may grow or shrink in fluid as they translate, distort, or rotate. And you can think of that because if you have an incompressible flow field, things are not going to get bigger or smaller because they're not going to compress. They're going to remain the same. Okay? But in addition to that, they're not going to change that overall volume. But they can translate, they can distort, and they can rotate because you can have volume in a plethora of different shapes, right? But in a compressible flow field, you get growing, shrinking, as well as the translation, distortion, and rotation. So here's the stream function in the Cartesian coordinates and the incompressible two-dimensional stream function in the Cartesian coordinates. So we have both of these, and you see the stream function looks like a little trident. That's what one student told me. And so here you just have stream functions, 2D incompressible Cartesian coordinates here, 2D incompressible cylindrical coordinates here, axisymmetric incompressible cylindrical coordinates here, and then 2D compressible Cartesian coordinates here. So it's just the definitions as well as the corresponding functions. Here are some streamlines on an XY axis, and the curves of constant stream functions represent streamlines in the flow, so pretty standard to what we've been looking at. And then you can see that they each have a subscript to name which they're working with because they are behaving different. And you can see this when you just take one arc. So you have an arc link here in reference to the change in x and y and a local velocity vector v along a two-dimensional streamline in the xy plane. And so you get this formula for along a streamline and then the total change of this streamline. And remember, this is the streamline. Okay, so curves of constant streamlines are streamlines of the flow. So the difference in the value of streamlines from one streamline to another is equal to the volume flow rate per unit width between the two streamlines. So you can kind of think of that like length times width, right? If you take it, it's not exactly, right? But the difference in the value from one to another, right, in between these, is equal to the volume flow rate per unit width. So you're taking that kind of on that XY axis. Here's formulas that correspond here. But here you have, for A, you have a control volume bound by streamlines 1 and 2 and slices A and B into the XY plane. So you see these streamlines and it's creating that boundary here. And then B is the magnified view of that region around the infinitesimally length change ds. So here when we're talking about the streams, when you are looking on an XY axis and you have a flow, let's just say is going normal to, right? Then you will increase going left, right? So going left on the XY axis if your flow is normal to, and you will go, this is 5 and 6 and 7 is how you can mark that. And then this is just a diagram showing you this. And this is just restating that. And then here it says when streamlines are far apart, so when we're talking about the distance here to here, right, is much further apart, or probably a better representation would be like here versus here, right? And so here, when streamlines are far apart, lower right of the figure, the magnitude of the velocity, which is the fluid speed, in that vicinity is small relative to the speed in locations where the streamlines are close together, like in the middle region. And why is that? Because of that convergence. So think of how a nozzle operates, right? So because the streamlines are in a converging pattern, or as they converge, the cross-sectional area between them decrease. So the cross-sectional area gets smaller, and the velocity must increase to maintain that flow rate between the streams. So here, it's getting much smaller, so that flow is starting to increase here. But here it's getting much bigger, right? So you don't need as much, and then it starts to converge again. Here are streak lines that are produced by the Healy-Shaw flow over an inclined plate. And we know that that is stationary because if it wasn't stationary, if it was moving, you would have a lot of turbulence here. But we don't have that, so we know that this plate is stationary. It's staying and it's flowing over. Streak lines model streamlines of potential flow over a two-dimensional inclined plate of the same cross-sectional shape. Here's incompressible planar stream functions in the cylindrical coordinates, and then incompressible axisymmetric stream function in the cylindrical coordinates. So these and these. And then this is just showing you the functions here that can be used and a diagram of the axisymmetric here. And then the rotational symmetry. So flow over an axisymmetric body in a cylindrical coordinates with rotational symmetry about the x or z axis. Neither the geometry nor the velocity field depend on theta, and thus u theta is equal to 0 because it's just not at play. Here's a compressible steam function. So we extend the steam function concept to steady compressible flow to two-dimensional flow in the xy plane. The compressible continuity equation in the Cartesian coordinates reduces to the following for steady two-dimensional flow here. And then we introduce the compressible stream function when we denote the stream P. So steady, compressible, two-dimensional stream function in the Cartesian coordinates here. And then here we get to the differential linear momentum equations, and this is Cauchy's equation here, and it's just sum of the forces, right? And so here is a note: positive components of the stress tensor in the Cartesian coordinates on the positive, which is right, top, and front faces of an infinitesimally rectangular control volume. The blue dots indicate the center of each face. Positive components on the negative, left, bottom, and back faces are also in the opposite direction of those shown here. And look, this is supposed to say red. It's supposed to say red. Sorry about that. So here's the derivation using the divergence theorem and the formulas associated with those, as well as the Cauchy's equation. And the derivation using an infinitesimally controlled volume. So inflow and outflow of the x component of linear momentum through each face of an infinitesimally controlled volume. The blue dots or red dots indicate the center of each face. So that's just showing you the direction. And then the net outflow of x momentum through the control volume. And then here is incorporating the gravity vector, but it's not necessarily aligned with any particular axis in general. And there are three components of the body force acting on an infinitesimal fluid element. And here's just additional formulas that are being used in the direction of each and how they are laid out here. And then a sketch illustrating the surface forces acting on the X direction due to the appropriate stress tensor component on each face. So depending on where the face is. And the red. I guess these used to be blue. The red dot indicates the center of each face, obviously. Here's additional formulas as well as, again, Cauchy's equation. And then an alternative form of Cauchy's equation, of course, we'll be working these. So I'm not going to go into detail in the formulas here. Again, derivation using Newton's second law. And here's the sum of forces equals mass times acceleration, right? And these fold out. And if the differential fluid element is a material element, it moves with the flow and Newton's second law applies directly. Force equals mass times acceleration. And then here for the x, y, and z component, because this is in a three-dimensional, the Navier-Stokes equation. And so here is a matrix for fluid at rest, and then for moving fluids, and then mechanical pressure. And so mechanical pressure is the mean normal stress acting inwardly on a fluid element. And when you see this inscription here, it's called the viscous stress tensor or the Derivative stress tensor. And so for fluids at rest, the only stress on a fluid element is the hydrostatic pressure, which is always asking inward and normal to any surface. That's what helps keep it together. Newtonian versus non-Newtonian fluids. So we kind of talked about that in the beginning. And so you have rheology, which is the study of the deformation of flowing fluids. And then in that you have the Newtonian fluids, and that's fluids for which the shear stress is linearly proportional to the shear strain rate. And so that means that it flows proportionally, right? So more shear stress, more strain rate. Less shear stress, less shear strain rate, right? So then you get non-Newtonian fluids, which is just the opposite. Fluids for which the shear stress is not linear related to shear strain rate. So you can't predict, right? So if you have something and you apply a shear stress to it, a great amount of shear stress, it's not going to behave as you would expect or linearly when it is receiving or showing that shear strain rate. Viscoelastic, a fluid that returns either fully or partially to its original shape after its applied stress is released. So you can think of a rubber band, right? So it's either going to return after you've pulled it, it's either going to return fully or partially really close to its original shape. Of course, the example of the rubber band is dependent on that you did not pull it beyond its elastic period and it fails. Some non-Newtonian fluids called shear thinning fluids or pseudoplastic fluids, because the more fluid is sheared, the less viscous it becomes. Plastic fluids are those in which the shear thinning effect is extreme. So you can see Newtonian, shear thickening, shear thinning, being a plastic, yield stress, and it's all plotted on a stress strain. So here, shear thickening fluids or dilatant fluids, the more the fluid is shear, the more viscous it becomes. So you can think, if he says, oh, quicksand, remember they always say, don't move, right? When an engineer falls into quicksand, a dilatant fluid, the faster he tries to move, the more viscous the fluid becomes and the quicker he sinks. And that's because it's shearing. He is moving, he is shearing the fluid. The derivation of the Navier-Stokes equation for incompressible isothermal flow. And so here, for a flow that is both incompressible and isothermal, then these are going to be constant, and therefore V is constant as well. Here's more formulas here, and the Lapéchin operator, shown here in both the Cartesian and cylindrical coordinates, appears in the viscous terms in terms of the incompressible Navier-Stokes equation. And then here is just the defining of the formula. And then the Navier-Stokes equation is an unsteady, nonlinear, second-order, partially derived equation. And it's the cornerstone of fluid mechanics. It has 4 unknowns, 3 velocity components, and a pressure, yet it represents only 3 equations, 3 components, since it's a vector equation, XYZ. Obviously, we need another equation to make the problem solvable. The 4th equation is the incompressible continuity equation. So this is just showing you how these formulas work together, the history behind them, and why they work together. And continuing on through these. And this is showing you on an XY axis, and then alternative forms of the viscous terms. Can be shown as this and this. So the differential analysis of fluid flow problems. So there are 2 types of problems for which the differential equations, continuity and Navier-Stokes are useful. And so they are calculating the pressure field for a known velocity field, and then calculating both the velocity and pressure fields for a flow of a known geometry and known boundary conditions. So you can, when an unknown pressure field for a known velocity field, and then the unknown velocity and pressure fields for a known geometry and boundary conditions. And then here it shows you 4 variables or unknowns for equations of motions. So here you have the calculation of the pressure field for a known velocity field. And so the first set of examples involves calculating the pressure field for a known velocity field. Since the pressure does not appear in the continuity equation, we can theoretically generate a velocity field based solely just on the conservation of mass. However, since the velocity appears in both the continuity equation and the Navier-Stokes equation, these 2 equations are coupled. And in addition, pressure appears in all 3 components of the Navier-Stokes equation, and thus the velocity and pressure fields are also coupled. And the intimate coupling between the velocity and pressure allows us or enables us to calculate the pressure field for a known velocity field. So this is just showing you how we can get to this calculation. The velocity field of an incompressible flow is not affected by the absolute magnitude of pressure, but only by pressure differences. And so that's when we're looking at, we don't care which particle you're looking at in a flow. We don't care, about those things. We care about the changes. We care about what is happening. And that's here. The velocity field in an incompressible flow is not affected by the absolute magnitude of pressure, but by only the pressure differences. And then here, as always, it's a good reminder to remember that when you go out into the workforce, you're not going to be working these all the time by hand, right? We're going to be automating a lot of this. And so the way that we solve them on paper, while it is very important, it may not even be the same pathway to which you solve them using a CFD code, right? Because a lot of them have algorithms. So they will change the way that the formulas like the Navier-Stokes equations work together. And so here, the most popular pressure correction algorithms result in a form of the Poisson's equation. Here it shows a 2-dimensional line vortex, and it's a simple approximation of a tornado. The lowest pressure is at the center of the vortex. Here's exact solutions of the continuity and Navier-Stokes equations, and so the steps associated with each. And so here, set up the problem in geometry. Sketches are always helpful, identifying all relevant dimensions and parameters, starting with what you know. And then 2, list all the appropriate assumptions. Say what you're assuming, say what you're approximating, simplifying things, boundary conditions. Simplify the differential equations of motion, continuity, and Navier-Stokes as much as possible. Make it simple. Integrate the equations, leading to one or more constants of integration, and then apply boundary conditions to solve for the constants of integration. And then, as always, verify your results as able. Here's interface boundary conditions. So at an interface between two fluids, the velocity of the two fluids must be equal. Okay? This is a good thing to know. In addition, the shear stress parallel to the interface must be the same in both fluids. These are great. And then here, along a horizontal free surface of the water and air, the water and air velocities must be equal and the shear stresses must match. However, since air is less than water, a good approximation is that the shear stress of the water surface is negligibly small. Right, so we just omit it. Here's the boundary conditions at water-air interface. And see, even if they're small, we still equate them as equal. Here's free surface boundary conditions. And then here you can see other boundary conditions arise depending on the problem setup, right? So if you need inlet boundary conditions at a boundary flow domain where flow enters the domain, we define outlet boundary conditions as an outflow, symmetry boundary conditions along an axis or plane of symmetry, and that's all here depicted. For unsteady flow problems, we also need to find the initial conditions, the starting time, and we usually do t equal to 0. So here looking at the Couette flow, it's the viscous flow between two infinite plates. The upper plate is moving and the lower plate is stationary. And then a fully developed region of a flow field in a region where the velocity profile does not change with the downstream distance. Fully developed flows are encountered in long, straight channels and pipes. Fully developed Couette flow is shown here. And you can see that the velocity profile is identical to that in X1 and X2, right? It doesn't matter because it does not change with the downstream distance when it is fully developed. So that is the caveat. It does have to be fully developed. Here, it's showing the assumptions that they are making when solving and the things that you can cross out. Of course, we will work these, and then you can get a final formula here for a pressure field. Same for boundary conditions 1, 2, final result for the velocity field, and then the shear force per unit area acting on a wall. So here is schematics. The first one is for incompressible flow fields without free surfaces. Hydrostatic pressure does not contribute to the dynamics of the flow field. So this is something that we know. And then the linear velocity profile of what we just covered, Couette flow between two parallel pipes. So we just went over that. And then stresses acting on a differential two-dimensional rectangular fluid element whose bottom face is in contact with the bottom plate. So these two contacts. And then here is talking about a rotational viscometer. The inner cylinder rotates at an angular velocity, and the torque applied from the viscosity of the fluid is calculated. And so here's that formula as well. And then it shows the direction in which torque is being applied. The Couette flow with an applied pressure gradient. And so here, viscous flow between two infinite plates with a constant applied pressure gradient. The upper plate is moving, the lower plate is stationary, so same dynamics, but just with that applied pressure gradient. And then here the velocity profile Couette flow between parallel plates with an applied negative pressure gradient. The dashed red line indicates the profile for a zero pressure gradient. So that'll show you for a zero pressure gradient. The dotted line indicates the profile for a negative pressure gradient with the upper plate stationary. So these are showing you the three different dynamics of how it would look. And here, just more formulas working through applied pressure gradient, result of continuity, result X momentum, Y momentum, the integration of X and Z, and then the final result, boundary condition, and then boundary condition 2. And then here's the non-dimensional velocity profiles for the Couette flow with an applied pressure gradient profile, and they are shown for several values of non-dimensional pressure gradients. And then the velocity profile for fully developed two-dimensional channel flow. Here's additional assumptions going forward: the result of continuity, the boundary conditions, velocity field, normalized velocity profile for oil film flowing down a vertical wall by gravity. And then here is just the normalized velocity profile of this example, so the schematic of the oil film falling down a vertical wall. And then through the examples 915 through 815, the equations of motion are reduced from partial differential equations to ordinary differential equations, making them much easier to solve because we like easier to solve. Here for the Poiseuille flow, the fully developed flow in a round pipe. So here is the geometry of the example that was covered before. Steady laminar flow in a long round pipe with an applied pressure gradient pushing fluid through the pipe. The pressure gradient is usually produced by a pump or gravity. So that is the parameters of it. You have the applied pressure gradient constant, the axial velocity, and then the viscous shear force, and that's per the unit area acting on a wall. Here it gives all of those formulas and the deductions that you can make. Continuing on through the boundary conditions, through the axial velocities, working all of those, which we will do. So not spending too much time in here, but it is nice to have these as a backup to just see how the formulas are flowing through. The viscous shear stress at the pipe wall, the viscous shear stress, of course, per unit area acting on the wall. And then here, just a caution for these. Exact solutions may be possible for laminar flow only, so it may be constricted to those. Exact analytical solutions for the Navier-Stokes equations, as in the examples provided here, are not possible if the flow is turbulent, which we saw in that example earlier on. Here is the Navier-Stokes equation as well in terms of incompressible flow solutions, in which the advective terms in the Navier-Stokes equations are zero. The equations become linear since the advective term is the only non-linear term in the equation. So if you take that out, then the rest of it becomes linear. Axial velocity profile, steady flow in a long round pipe with an applied constant pressure gradient pushing fluid through the pipe, so just the schematic there. And then here's another one, pressure and viscous shear stresses acting on a differential fluid element whose bottom face is in contact with the pipe wall. Note that we are ignoring gravity in this case, so that's a good assumption or note when you're solving yours. You're ignoring gravity in this case, otherwise pressure would increase in the direction of the gravitational acceleration because that force would be applied. Control volume used to obtain 15, and then example 918 by an alternative method. And then here, equation of the day, as if you needed any more, the one-dimensional diffusion equation is linear, but it is a partial differential equation, a PDE. It occurs in many fields of science and engineering. And then here it goes into the differential analysis of biofluid mechanic flows. We talked about that briefly. We talked about the blood flowing from different arteries. We talked about the heart, the cardiovascular system, and how you have a ton of different systems within your body that is for that biofluid mechanics flow that you could study in here, but we tend to limit it to the cardiovascular because it's the easiest to understand and tie together. And so something important, the Poiseuille fluid approximations hold true for standard pipe flow with most water systems. However, when applied to blood flow in the human body, the approximation must be closely monitored and evaluated for their applicability. So they're not proven to hold true for blood flow in the human body. Traditionally, as a first order attempt, cardiovascular fluid dynamists have used the Poiseuille flow derivation to understand blood flow in arteries. Okay? And so it can provide the engineer only with a first order approximation for the velocity and flow rate. And then here it's important to examine the main approximations used to arrive at the Poiseuille flow. So you talk about approximations about the fluid, which is the blood. The fluid will remain incompressible. The flow will continue to be laminar, hopefully not turbulent, right? And the gravity remains negligible. Approximation of the fully developed flow will also remain through its reality. This is not applicable in the cardiovascular system. And then based on all of those approximations, this leaves the other main approximations as steady, parallel, axisymmetric Newtonian flow, and the pipes approximated as rigid circular tube. And then here you can see the flow waveform created during an injection of a ventricular assist device in a mock circulatory loop. This is similar to a waveform created during the left ventricular ejection. And then here is the anatomical figure illustrating the ascending aorta, aortic arch, and the descending aorta coming from the left ventricular. So it just demonstrates how the aorta moves towards the spine of the cord. And then here you have some findings, right? Fundamentally, to model the blood flow through the arteries, the steady flow approximation is inappropriate, making the modeling blood flow through Poiseuille unsuitable for just one approximation alone. Rigid circular tube approximation is equally as inappropriate because our veins are not rigid circular tubes, right? With respect to parallel flow and axisymmetric flow, these both can be invalidated. So this is great in some industries, but it can't be characterized or applied to every flow. You really have to look at the individual boundaries and individual circumstances and parameters and environment and everything that is happening on the system that you're looking at to find out what is most appropriate. So here, assuming all values are the same in the velocity equations, the pipe is the same diameter, all of those things that we just talked about are same. The pseudoplastic fluid causes the velocity profile to be more blunt compared to the parabolic profile generated for the Newtonian fluid. And so you can see that even if those were all the same, they could still be different depending on the fluid. So here's a summary. This chapter, like many of the other ones, are best comprehended, in my opinion, through working the problems, especially because it's the analysis of. So this was really just giving the formulas. They really need to be worked. But I do have a small video that will help show you the difference between the Newtonian and non-Newtonian fluids.
A fluid with constant viscosity coefficient mu at any strain rate, represented by the velocity gradient du dy, is called a Newtonian fluid after Sir Isaac Newton. Water, air, and many familiar fluids behave according to this simple Newtonian law. However, some fluids, such as suspensions of particles or polymers, do not behave this way, and they're called non-Newtonian fluids. This thick solution of cornstarch in water is an example of a non-Newtonian shear thickening fluid. Hit it with a hammer, and it acts like a solid. Deform it more slowly with your finger, and it acts more like a liquid. Silly putty is a shear thickening memory fluid. You can bounce it around and it remembers its spherical shape. Let it sit for a while, though, and it spreads out like a viscous liquid. Other non-Newtonian fluids are shear thinning. It takes some effort to get them flowing. Ketchup is a famous example. You have to hit the bottle hard enough to exceed the ketchup's shear threshold, whereupon its viscosity falls and it begins to pour. Paint is another example of a shear thinning fluid. It's viscous enough to stick to the brush because the applied shear stress is small. But its viscosity drops dramatically as it's sheared, so we can apply it to a wall in a thin coating.